Hey guys, it's Miss Marsh. So what I want to do is give you some more explicit notes dealing with functions, how you pull important information from the graph and or the equation. So a lot of these notes you can put on page 6. Some of it will line up with the titles or headings that are there on page 6. Some of it you might just want to use some of that open space and the bottom half of the page, just so you can kind of keep track of things. So some important things that we need to know. Degree of a function, something we probably have some familiarity with already. This is simply the highest exponent in the function. Determining whether a function is even or odd. This is simply based on if the degree is even or odd. So if your highest exponent is a 4, 4 is an even number, so the function is even. If the highest exponent is 5, 5 is an odd number, so the function is odd. We use whether something is even or odd to help us in determining certain things about the graph. And so that's part of what we'll talk about here momentarily. The number of turns on a graph, this simply refers to how many times a graph changes from moving between positive and negative directions. This is always 1 less than the degree. So if you have a degree of 4, there's going to be 3 turns on the graph, or 3 times that it shifts from positive to negative. So what I've done is, as we go through each piece here, I'm going to go through those items using an example at the bottom. This is just an equation and the graph of a polynomial function. So if we look at this and you were asked about the degree of the function, you're looking for that highest exponent, right? So this would have a degree of 3. 3 is an odd number, so this would be an odd function. And then when you're talking about the turns, I can look at my graph and say, okay, here is 1 turn where it moves between going from positive down and then turns to negative. Here it was going negative, now it turns and it's going positive. So notice there are 2 turns on this graph, which is 1 less than the degree on the graph. If at any point, guys, as I'm going, you need more time with items on the screen, just make sure you hit pause so you can copy things down. When we're talking about a graph, one of the main things we talk about is what's known as its end behavior. This is literally how a graph behaves at the far left and right sides of the graph, meaning its literal ends. The ends of your graphs of polynomial functions are going to go off towards infinity. Okay, they're just going to either go up or down literally forever. So the idea is, in which direction is it going forever? Even functions, your ends will go in the same direction. So either both ends will go up or both ends will go down. If it's an odd function, the ends go in different directions. So this is where knowing the degree and whether it's even or odd comes into play, so that we can then determine certain things about our graph even before we make it. What should those ends be doing? Same direction, different directions. The way we write this is we talk about x and y going to positive or negative infinity. So if you think about the left side of the graph, on the left side of the graph, your x-axis is going towards negative infinity, right? It's going to the negative numbers on the left side. So as x approaches negative infinity, your y will either approach positive or negative infinity. If it's going up, the y is going to positive infinity. If it's going down, it's going to negative infinity. On the right side of your graph, that's where your x-axis is approaching the positive values. So as x approaches positive infinity, again, your y is either going to positive or negative infinity. Positive if it's going up, negative if it's going down. So if I take this idea of end behavior, okay, part of it I can pull from the graph, and part of it we would be able to pull from the equation if we didn't have a graph. Okay, so for example, the fact that my equation, before I even look at my graph, the fact that my equation is that odd degree, right, that I have that degree of 3 here, that tells me that the left and right sides of my graph are going to go in different directions. So one side should be going up and one side should be going down. When I look at the graph itself, on the left side of my graph, as x is going in that negative direction, notice my y is going in a negative direction as well. So this would give me that x is approaching negative infinity, right? Because that's what it always is on the left side. And you would say that y is also approaching negative infinity. And then on the right side of my graph, x is going positive, and notice that y is also going positive. So same thing, except now they're both positive. So x is approaching positive infinity as y is approaching positive infinity. So you would write one of those statements for each side of your graph. Part of what comes along with the end behavior also deals with your lead coefficient. This is the number in front of the variable with the highest power. This gives the end behavior on the right side of our graph. So in other words, what's happening when x is approaching positive infinity. So if it is a positive lead coefficient, that means we're going to go up on the right side of our graph. And if it's a negative coefficient, it's going to go down on the right side of our graph. This is going to allow you to know the left side based upon even or odd, because either it should go in the same direction or opposite direction. So for example, let's say I didn't have the graph to this function at all. This graph wasn't even here. When I look at the example of the equation, again, we have this odd degree. My lead coefficient is this positive 2. So because it's positive, I know that this is giving me the fact that on the right side of my graph, it's going to go in a positive direction. So in other words, even if I didn't have this graph over here at all, the positive 2 tells me that as x approaches the positive infinity on the right, y would have approached the positive infinity because it would be going up. And then, because this is odd goes in opposite direction. So because this y was going positive, I would know that the y on the left side of my graph should be going negative. So even without the graph, just from the lead coefficient, right, positive or negative, meaning going up or down on the right, and then whether this is odd or even, should it match or should it go in opposite directions. So you're still able to determine end behavior without actually making the graph. And so that's why before you even make a graph, you can have an idea of what it's supposed to look like, because you'll have an idea which direction those ends are supposed to go. Likewise, we can talk about the location and the number of roots. And so we did this a little bit when you were graphing from factored form, because the easiest way to graph from factored form is to first pull those roots or those zeros from the factors. The number of real roots, which is where it crosses the x-axis, is less than or equal to the degree of your function. Okay? The number of total roots is always equal to the degree of your function. So sometimes these will be the same because all of the roots will be real roots crossing the x-axis. Sometimes they will be different. If they are not the same, then that means your graph or your equation has imaginary roots. And so this is where you're going to link back to your imaginary numbers from your previous unit, and that's something you'll get to later in this unit, talking about how we find the zeros that are real and are on our graph crossing the x-axis, and where are those imaginary roots where it's not crossing the x-axis, but it's still considered a root or a zero. So when you're looking at a graph, the easiest way to find your real roots is simply count the number of times it crosses your x-axis. So when I look at my graph here, right, there are 3 places it crosses the x-axis. So I would say, 3 real roots, right, or real zeros, either one. Excuse my kindergarten handwriting, right? When I look at my degree, the degree was 3 and I have 3 real roots. So this is where the total roots and the real roots are matching. If I had a degree of 3, but maybe I had a graph that only crossed my x-axis twice. So this could happen, for example, if this is my x-axis, maybe I had a graph that instead of crossing the x-axis, it just sort of came down and kissed it. So it touched it only twice, right? It would have sort of one here and one here. Then there would be 2 roots, but this could actually be graphed from an equation that has a degree of 3, and this would say have one imaginary root. One last thing that we deal with when it comes to our graphs is whether they have relative maximums and minimums. So this is your point where the graph changes from increasing to decreasing. This is, oops, I just realized. Okay, sorry guys, I just realized I had missed something on my slides. Let me try that again. You have relative maximum minimums. A relative minimum is the point where the graph changes from decreasing to increasing. A relative maximum is the point where the graph changes from increasing to decreasing. Basically, guys, you're looking for the relatively highest point and lowest point on your graph outside of where it goes off into infinity. So when I'm looking at my graph, right, this point up here where it turns from going in an increasing direction and it turns down to going in a decreasing direction, this point here would be a max. And then down here at this point, this is going to be a min because this is where it's going from a decreasing direction, turns and goes up into an increasing direction. So depending upon where those points are on a graph, you can actually find them as ordered pairs. Those are things we typically find from the graph itself or something you find when you make, say, a table of values. So here's what you're being asked to do at this point. Some of this information is going to come into play as we keep going in the unit, and some of this information you need literally today. So on page 7, these are the instructions. State the end behavior, determine if the function is even or odd, state the number of real zeros. So I'm just using the same graph I was using over the course of my slides. So this is not on page 7. I'm just going to use the same instructions. So state the end behavior. So we did this, right? So as x approaches negative infinity on the left side, my y is also approaching negative infinity. As x approaches positive infinity on the right side of my graph, y approaches positive infinity because it's going up. Determine if the function is even or odd. So you can do this by counting the zeros. There were 3 zeros, which is odd. You can also do this by counting the turns and adding 1. So there were 3 zeros. So good odds I have a degree of 3. There are 2 turns, so that confirms that I have a degree of 3. Because sometimes you have those imaginary zeros, checking with the turns can always be a good idea. It does want you to state the number of real zeros, so 3 real zeros. So those are the items that these instructions specifically want. We could also talk about whether it's even or odd. Obviously, now that I know the degree, I know it's odd. We could talk about a leading coefficient being positive because I'm going up on the right. So that's where some of these other things will come into play. I hope this helps. You're taking care of all the questions on page 7 and uploading for credit, guys.